In the previous video, we talked about beta decay, or the production of beta particles when a nuclei is not stable, right? So nuclei that are above the belt of stability tend to undergo beta minus decay. They lose electrons, negatively charged particles, and they convert neutrons into protons. Nuclei below the belt of stability undergo beta plus decay. They lose positrons and convert protons into neutrons, right? So beta minus decay, beta plus decay are both kind of related to this belt of stability. The other type of unstable, so there's one more type of unstable nucleus that we need to talk about, and this is nuclei with more than 83 protons. And basically, nuclei with more than 83 protons don't have stable isotopes. All nuclei above 83 protons tend to be unstable. They tend to be radioactive. Now, they can be very slowly radioactive and not produce a whole lot of and not decay very quickly, but they still are unstable, right? So nuclei with more than 83 protons tend to undergo alpha decay. And so the goal here for nuclei with more than 83 protons is they need to lose, right, to become stable, they need to lose both neutrons and protons. They need to lose both neutrons and protons. So they don't even have to worry about the ratio between neutrons and protons. They just have too many subatomic particles in their nucleus. They have too many neutrons, too many protons. They just need to get rid of them. And so what they do is they undergo alpha decay, in which they lose 2 protons and 2 neutrons at a time. And so we lose these helium atoms, which is known as an alpha particle. So I think in Gen Chem 1, you guys probably learned about the Rutherford experiment, where he fired these atoms at, or he observed going through a gold foil thing and all of this kind of stuff. The thing that he fired at the gold foil were these helium atoms, these alpha particles, because they're very easy to kind of generate because you use radioactive compounds in order to do that, right? So these alpha particles get used quite a bit. They're very easy to produce if you have nuclei with more than 83 protons, right? So in the belt of stability that we drew before, one second, there we go. When we get out to 79, 83, right past that, there really are no stable isotopes. And so now the belt of stability no longer really exists. Instead, we just have these things that have way too many protons and way too many neutrons. And so to get back into this stability kind of the area where we can talk about the belt of stability, they need to lose some of both. And they do that by losing helium atoms, or alpha particles. And that is pretty easy to do. You know, I thought I wrote down some examples of this. Yeah. So an example of this would be uranium-238. Okay. So we've already talked about 235 and 236. Uranium-238 decays by producing alpha particles. And so we get to 90 and 234, and this is thorium. So we create thorium-234. Thorium-234 continues to produce more alpha particles. And basically you keep losing helium atoms, alpha particles, until you get down below 83. And this is one of the reasons that lead, which has an atomic number of 82, is so common, right? Lead is the end product, is the end of many alpha decay processes. Right? You keep losing helium nuclei, you keep losing protons and neutrons until you get down to 82, and you get the various isotopes of lead. Right? So this is why lead is so common in the Earth's crust, much more than one would expect for an element this large. It's because all the radioactive elements, all the elements above 83 in atomic number, are slowly decaying to produce more and more lead as time goes on. Okay? All right. I did that. This is a different class. think we're on to rates of decay. So the last type of thing that I wanted to talk about in this video, and I think I've done it, is alpha decay. So we have three types of decay. So we've got all our atomic particles that we talked about. We have our nuclei with protons and neutrons. We have neutrons, positrons, and electrons that we have to worry about. And then we have a belt of stability that tells us whether our compound is likely to undergo beta decay, beta minus or beta plus, depending on if it's above or below the belt of stability, or if it's just a huge nucleus, it undergoes alpha decay and produces helium atoms, right? So we can kind of predict what's most likely. We can balance equations. We can interpret the belt of stability. These are the essential skills that we're going to do. From here, we're going to move into what are the types of things that we worry about with these reactions, right? And mostly what we worry about is the rate of these reactions. How quickly are we producing alpha particles? How quickly do we produce beta particles, et cetera, et cetera? And to do that, we're going to revisit the half-life equation from way back in September when we talked about rates of reaction. So we're going to start to talk about half-lives in the next video.